Are people still coming? Yeah, give them 2 minutes. Do we have the presenters? Jim is there. Bob is there. You are here. Jim is doing this? No. Who is doing this?
Yeah, but half of the by number.
Oh, okay. Engineer.
Yes. Yeah.
I guess we can do it.
Yes, Mihia is not here.
I'm not sure if she will come. Where? Do you know?
She's supposed to come. She's ready, but I think eventually she will come.
Yeah, okay.
But maybe, people still coming.
Yeah. Would you do the introduction?
Yeah.
Should I do that?
Oh, which introduction?
Well, starting with these slides.
Oh, okay, I can. Okay. Shall we start? Okay, let's start. So this is TCPM working group meeting, TCP maintenance and minor extension working group. Please make sure you are in the right room. And okay, this is user node well, and I think you're already aware of this one, but just in case, by participating in the IETF, you agree to follow IETF process and policies. And if you have any concerns about it, please check this note well very carefully, and you can find the same contents on IETF website. Okay, moving on. And we have note takers.
Do we?
Do we?
No.
Okay. Could anyone volunteer note taking? Thank you, Gori. And can anyone take care of Java?
I found some.
Okay. Thank you so much.
You do.
And this is just a usual reminder. During the meeting, when you speak up the microphone, please state your name so that note taker can track your name. And then when you submit your internet draft to this working group, please make sure include a TCPM in your draft name so that chairs can track the status of your draft. Okay, moving on. And so this is today's agenda. We are starting from working group status from chairs. And then we have 2 working group items presentation. First, Yu-Chung will talk about RAG draft update. And after this, Bob will talk about accurate ECN draft update. And after this one, we have 2 individual presentations. Yoshi will talk about his new internet draft. And then we have another individual presentation, making TCP faster and cheaper for application. And this talk will be done by Soy and Yu-Chun. And after this, we have other draft presentations, TCP constraint and no network. And actually, this draft is a working group item in LWIC working group. But this draft is related to TCP. So TCPM chair and LWIC working group chair agreed to run working group RASTCO on both TCPM and LWIC working group. So this presentation gives some kind of heads up before this draft go to working group RASTCO. So this draft is not running working group RASTCO right now, but beforehand, we want to give you guys a heads up. So if you are interested in this draft, if you want to say something on this draft, please read this draft and provide your feedback on this draft. That's why we have this presentation today. Any question to the agenda? Any comment, questions? Okay, moving on. Okay, let's start from status of document. And since last IETF, we have finished 1 draft. We have submitted alternative backup draft, the alternative backup ECN draft to the IETF in last May. And thanks so much for your cooperation. And then we have 6 active working group items and accurate ECN draft. This draft has been updated recently, and then this is one of today's agenda. And next one is TCPM RAG draft. This draft has been updated, and then this is also one of today's agenda. And 793-bit draft, this draft has been updated. Unfortunately, the author cannot come to this meeting, but we have received a slide from the authors, so we will talk about it on behalf of the authors. And not yet. And then TCPM converter draft, and this draft has been updated recently, but according to the author, it's a minor update. And then EDO draft, there is no update so far. According to the author, they are doing some ongoing experiment on this draft. And the last one is generalized ECN. And unfortunately, this draft has been expired for now. So we expect author to update draft very soon. That's the status of the working group item. Any question, comment about the active documents? Okay, moving on. Okay, so this is a slide for 793-bit status. So I will speak about it on behalf of the author. Thank you. And 2 weeks ago, revision 10 has been submitted. And this is updated related to diff-serve and security consideration. And then thanks for very good feedback from Yuchun, Joe, Gori. Thank you so much. And then the remaining item is updates some conformance checklist at the end of the document, just like RFC 1122. That's the plan. And this will be done in July. And okay, go Jana.
Jana Iyengar, question on the previous slide. You said on the active documents.
Okay.
I was looking at this document, RTO consider, and I just realized yesterday that it's actually a working group document. It's expired, but it's not on this list. So I wanted to ask what the chair saw the status of the document was.
Okay, good question. And so we have talked about this draft in the last IETF, and then this draft has been expired. And then one plan, maybe we can find some kind of editor, but some editor, whoever will be an editor, it will be very tough job. You have to exchange also email to authors, and then you have to reach to the conclusion. So it needs strong power. So if someone want to volunteer for the editor, that would be really great. So Jana, you want to volunteer for editor?
So I spoke with Mark yesterday about the draft,
Okay.
and I'm coaxing him. I'm trying to convince him to get an update out.
Okay.
It's a 4-page document. He can finish this up, but
Right.
if it becomes difficult, then I'm happy to help him wrap it up.
Yeah. So
But I think-
previously, chairs tried a lot actually, but for some reason, he doesn't respond to chairs. So if you can help us, that would be really great.
Happy to do that
Okay. So you want to be an editor? You mean, if necessary?
if necessary. I don't think it's required at this moment, but
Okay.
I'm happy to
Okay.
to help
We
push
will
this draft
contact you
forward.
later. Thanks so much.
So I think one of the one of the issues is that what's in the document has to reflect the working group consensus,
Yes.
and this is what was hard to get in the past. Not making any future statements, but if
Fair
you
enough.
would be willing to talk to him,
And I'm happy to present, and I'm happy to do the things necessary to move this draft. I think it's a useful draft.
we
I
think
think
that too.
yeah.
However,
Yeah.
things are like things are.
Yep. Yeah, I'm happy to help move this forward.
Okay. That's good.
Mia Kulevind. So as far as I remember, and that was a while ago, I think there was a lot of back and forth off list with Mark, and I think we actually got to some kind of agreement. So if you want to help, we need to pick out those emails, figure out what the agreement was, and then we can involve you. And I mean, Michael Scharf was mainly involved in that. So
Right.
Thanks, Jana.
Okay. And any question about 793 base status? This is in the middle, so I haven't finished it yet. So this is 793 is very important document for this working group. As you know, this is 793 base. So it could be more important for entire IETF or entire internet. This is 793 base again. And I know this is very, very long draft, 100-page draft, but and then we already get some nice review from the people from time to time, but it's small subset of people. But if it would be really good if we can get broad reviews. I know this is long draft, but if you can just read one section and provide feedback, that would be really, really great. And then I cannot say exact time schedule, but I think this document is step-by-step approaching the working group RustCo. So before we start running working group RustCo, we would like to make sure there is nothing left. So if you have any concerns about the current status of the draft, and if you think something should be done before the working group RustCo, or if you have some serious concern, some part of the draft, please speak up. Please speak up or send a message on the mailing list. That will be very helpful for us. Any comments, some questions? Okay, just if you have time, please take a look at the draft and then provide a review to us. Again, this is important draft for us. Thank you so much. Okay.
Any questions? If not, then it's rec time.
Hi, everyone. I'm here to give an update of the new RAC draft. My name is Yu Chon, and this is a work jointly with my colleague Neil, Nandita, and Priya at Google. Next slide, please. So I think most people here are familiar with RAC, but just in case you're first time you hear about it, RAC in a simple way is it's trying to detect loss efficiently while tolerating a small degree of reordering. And very conceptually, you can think of every packet you send, you arm a timer with it. And when the timer fires, you retransmit the packet. So how long do you arm the timer? That's the tricky, the part that RAC does is that it uses the mostly recent measured RTT. And you can imagine every act comes back, it updates all the timers. That's for all the pending packet that have been sent but not acknowledged. That's the very super high level of it. And then, so you don't need to count the number of dewbacks or anything because it's all timer based. And if you think of fast recovery, the 3 dewback rule is similar to what RAC is doing, which is, okay, when you get 3 dewback, that means sort of you get 3 RTT measurement, and then you just send the unact packets right away. And it's kind of like you're trying to repair that within a round trip, which is what RAC is trying to do, except he waits for the timer is armed so that it's the timeout is an RTT plus a small reordering window to tolerate the reordering. Next slide, please. So in the last meeting, the main discussion is that there is a lack of design rationale of the RAC reordering window because the old draft is just says, okay, a quarter of RTT, empirically tested, seem to work fine. But the concern is that, well, how do you detect reordering? And how do you really handle reordering? Are we going to make TCP so tolerant to reordering that now the network gears will start reordering packets to hell, or send one packet over the moon and the other over your local area network? So first thing first is that we need to define how reordering can be detected, because the previous draft doesn't really talk about it. He just cites you can implement some algorithm, and here is the algorithm in the new draft. In a nutshell, it's very simple. If you want to detect reordering, you just look for out of order delivery, right? And with TCP SAC, basically you introduce a new state variable that you remember the highest SAC sequence you have seen. And now when you get another SAC, then you check with this highest SAC sequence. If it's below the highest SAC sequence, which we call that FAC, forward ACK, then this sequence has never been retransmitted. And then this is clearly that some reordering has happened because the packets were delivered out of sequence order. And then you simply remember that, okay, I have seen some reordering. We don't measure the reordering degree. We simply remember this incident in a state variable called RAC reord. In addition to that, if the connections support DSAC, then you can further use that to detect reordering. Because if the packet has been spuriously retransmitted, the previous technique wouldn't work, because you weren't sure if the SAC is sacking the original one or the retransmitted sequence. But a DSAC clearly indicates that, hey, if you have retransmitted this packet, and also I get a DSAC that's acting the sequence, that means this retransmission is spurious, and you wouldn't have done that. The original one has been delivered. And with that, you can say, okay, that's also reordering. So DSAC cover the case where they say your reordering window is small, and then you spuriously fire a retransmission. And so the SAC sequence doesn't give you much clear picture of whether this reordering or not. But if the connection support DSAC, you can detect that. And the good news is that the major stacks all support DSAC. Windows, iOS, and Linux all support DSAC. Next slide, please. So now we can detect reordering. We put this design rationale for rack reordering tolerance. And first thing first is that today, if you just reorder packets as however you like it, send it over n different paths between source and the sink, then it actually already causes a lot of problem, despite whether you use rack or not. First, the biggest problem is on the whole stack. That is a very high CPU cost because now the GRO, the receiver offload wouldn't work. Because typically the receiver offload at the host requires receiving continuous packets of continuous sequence. And on top of that, now since you don't send these big jumbo frames to the receiver TCP stack, and these are all out of order packet, the TCP stack requires you to send immediate ACK for every one of them. So let's say you send n packets, they are all completely permutated and reordered, then you end up sending n ACKs instead of one in the typical case. So this also adds pressure to the sender because now the number of ACKs you need to process is a lot higher. And in our test, if you do this in, say, in a data center with extremely short RTT and very high bandwidth, over 1 Gbps, you will see this very significant CPU increase. So that's the first problem with, highly reordered network. The other one is congestion control, right? If you send packet over very disjoint paths, and most TCP congestion control assumes that the feedback you get is from the same bottleneck. And in this case, it's from two different bottlenecks. Essentially, TCP congestion control just won't work very well. And there are problems to solve that. I'm just saying that if you just run it without any change to congestion control on a highly disjoint path, it won't work well. And the last one is the loss recovery. You can always wait longer to tolerate very high reordering if you know that the network primarily reorder instead of loss. But the consequence is that, if you do have packet loss, then you will wait longer to recover the packets. And it's always sort of a dilemma for how long do you set the reordering window. You can never get the best reordering tolerant and the best loss recovery latency. So with all that issues, what rack is trying to do is to tolerate small degree of reordering on slightly diverse paths. And the most common thing is the router parallelism that within a hub, between the ingress and the egress port, there are multiple hubs to traverse. This is not necessarily like a router. It could be a load balancer or even just, any kind of intermediate node that trying to forward between A to B. And the packet may traverse slightly diverse paths. And typically, the traditional approach is you put a reordering buffer at the egress. But a lot of time, reordering buffer always costs memory, and you have to add a lot of logic in the node to deal with this. So sometimes people hate to do that. I mean, a lot of router designers hate to deal with TCP reordering. And so they might try to do something about it to a limited degree, that you're trying to keep reordering to a certain extent. But out of that, they will just let packet reorders. The other common thing is the L2 retransmission for wireless, where the wireless trying to bunch up n TCP packet and send it over, and maybe 3 of them out of n because of channel noise couldn't get delivered. So the link layer will retransmit these 3 packets. And if the receiver NIC or driver doesn't handle this reordering buffer well, then they will try to upload the n-3 frames up to the TCP stack. And that's why you observe reordering. But the sort of the thing is that these reordering are usually very small in terms of the actual RTT. And that's what rack is saying, okay, we just need to weigh a fraction of RTT, but up to the maximum of the pass. That's the rack reordering window. He cannot handle anything beyond that. Next slide, please. So this is what's written in the draft, and so people can take a look at what exactly did we put on the mandate of the reordering window algorithm. Initially, when you start the rack reordering window, the extra time beyond the RTT you want to wait before you retransmit a packet should be set to a fraction of the round trip time. And by round trip time here, I don't mean the pass 1 or pass 2, because I cannot distinguish how many passes it actually travel. It really just means, okay, the overall average round trip time of this pass. So you can imagine if the round trip times are highly disjoint and highly diverse between different paths, then it won't work well. But again, as I said, it's not designed to work well in those environments. So initially, we start with a small fraction. In our draft, we just make it a quarter, but this could be, it's always bound to change as technology evolves. And until the reordering out has been observed using our reordering detection, we will continue to honor this classic 3-due back rule for 2 reasons. One is that because of you need to wait a little bit longer, and that means if in a data center setting when the RTT is very small, say 20 microseconds, when there is no good ways today to mount say 5 microsecond timer with a lot of flows. So simply counting still offer a great advantage in this this environment. And the other key reason is that for compatibility reasons, that firewalls, who knows, like intrusion detection system, could still be using these rules. And if just for safety, we say we'll continue to honor this 3-due back. And it's very simple to implement, and every implementation has them anyways. One simple way to do that is to, in rack, you can just set the reordering window to 0 when you see 3-due back. Bob?
Hi, Bob Briscoe from Cable Labs. I wonder whether you could say that initial reordering window. I mean, you've said it's a should to start with, but maybe you could suggest it should be 3-due pack, the maximum of 3-due packs, or a certain fraction of the RTTs, so that in the future, when it is possible to time precisely, you haven't essentially you're losing a lot of the benefit of using something that's purely time-based if you say, oh, actually we start by counting, what I mean? For when things get really a lot faster in the future.
I see. Yeah, that's a good point. I think maybe we can add sort of a note saying that, in the case where, timer constraint is no longer an issue, then the 3-due back rule may be overridden. Yeah.
I was thinking like, I don't know, what RTT divided by 16 or something, the max of RTT divided by 16 and 3-due pack as the,
okay.
Something like that.
Yeah. That'll work. And the third rule is that we don't want to just have a start with a fraction and then statically set this window. So we would recommend that the implementation should also use DSAC, as a indicator of the spurious retransmit, that okay, your reordering window is too small, so we have spurious retransmit. To adaptively increase the reordering window, we don't mandate like exactly how you should adjust or adapt to this reordering window, but just saying that you should take this feedback of okay, you made it, you made the window too small, and then you should increase it. And the last one is probably very important, that the reordering window must have an upper bound, and it should be set to 1 round trip. And again, this round trip is intentionally vague, a bit vague of what exactly is the round trip. In our implementation, what we use is the smooth round trip time average, but you can use the most recent one or a window max filter of the most recent RTT. We don't put like exactly how you should do that.
Christoph Bosch. I actually have a question about the bounded reordering window. Because, like, for example, with your layer 2 retransmissions, you could have a bigger reordering window than the RTT itself. And do you have any thoughts on that?
Yeah, so let's say the RTT is actually going to increase for those retransmitted packets, right? Assume that you measure those packets, the round trip time of those sort of retransmitted packets, and it could be a lot longer than the, say, propagation delay. And in this case, I think if you use some kind of like smooth average, which take account of all these packets, then you should still work to a certain extent, because the smooth time, the SRTT is always sort of biased towards the longer samples. Yeah. Yeah. But I think in this case, we just want to keep it sort of loose so that, you know, the implementations can sort of improvise based on the particular situations he needs to fix. Next slide, please. So with all that said, how do we really compute the reordering window? This is the exact formula we use in our Linux implementation. So start with, do we detect reordering or not? If we haven't seen reordering and we are already in loss recovery, since we are already in loss recovery, that means we feel like this, in this situation, we are going to optimize to speed up the recovery. We believe that we have made the right decision. This is a loss, not reordering. So we're going to set the reordering window to 0 and really fire up the retransmissions very quickly. Other than that, we'll use, again, like I said, the 3 due-back rule, which is rack due-back ratio is 3. So if more than 3 packets have been act out of order, then you are going to launch the loss recovery process to repair the packets. And if we have seen reordering, so none of those cases match, and we have seen reordering, we are going to set the reordering window to 1/4 of the mean RTT. And we have this multiplier called reordering window increase, which will linearly increase. And this reordering window increase state variable will be adjusted based on have you seen DSAGs in the last round trip or not. Because every round trip you have seen a DSAG, you are going to increase this multiplier. Ian?
Ian Sweat, Google. This is a clarifying comment, and it's not a complaint about the slides, but I just recently got some fairly decent data that kind of indicates that maybe min RTT over 8 might be a better starting multiplier, especially since you're doing an adaptive back off. And I'll be presenting those at MapRG, and they should already be uploaded online if you want to take a look.
Yeah, so I think 3 meetings ago, we actually had ran an experiment to compare 1/4 on an 8. We don't really see any difference for TCP data. And again, I think it's fine. I'm fine changing it to 8. We don't see any data, so you can say one way or the other. And we specifically leave out in the like rack does not mandate you have to be 1/4 RTT, so that, you know, the implementation can always choose the best value they believe is right. Yeah. So, and then the last line is simply the reordering window is unconditionally bounded to the SRTT value.
Michael Jackson, so just a suggestion, replace 4 by a named constant like your dupe thresh, and say you may say set it to 4 or whatever. Then it's clear what this.
It's a variable. Okay, yeah, sure, can do that. It's a good point. Next slide, please. Okay, so I've talked about all the drafts update, and Linux 4.18 today fully implement what I just talked about in the draft. And it's on by default. So the old RFC 6675, the SAC-based recovery, which primarily use due-back threshold, is actually now disabled. So the latest Linux actually use rack as the sort of the one and only fast recovery mechanism. And overall, we have reduced the number of heuristic in Linux about loss recovery from 10 to 2. It's rack TLP and FRTO. And FRTO includes the basic RTO, of course. And the overall, the algorithm development and implementation has been concluded. We don't plan any major development work, maybe bug fixes. And so I think that at least we have an implementation fully implement the draft. I believe that Praveen told me yesterday that Microsoft is still trying to catch up. It's implementing the -02 draft, but they are going to sort of implement the 04 very soon. And that's it. That's my talk. Any questions, comments?
Jana Iyengar, this is perhaps a question for the chairs. Is this ready for last call?
I think this draft has been updated just 2 weeks ago, right?
Yes.
And also Praveen tried to implement this draft, and then he might come back with some feedback. So maybe we can wait a little bit. But I think this draft is now getting good shape. So I think working group last call is close, but I would like to wait a little bit more.
Okay.
Okay, sounds reasonable.
So it's actually a call for implementers to look at this document, implement it, and provide feedback.
Okay. Thank you.
So thank you. Bob? Oh. He started moving.
This is as high as it goes. Excuse me, I've never been too short before. No, can't do it. Okay. Right, this is Accurate ECN. Just recently updated this draft. Can you move on? Thanks. A quick recap. Explicit congestion notification in the IP header in that table there. Has feedback defined in RFC 3168 for TCP. It's not only intended for TCP. Well, ECN is not only intended for TCP, but it was defined at the same time as IP. And the problems with that feedback were that you could only get one feedback per round trip time. And then that was because the receiver repeated this echo congestion experience flag for reliability until it got a acknowledgement called congestion window reduced from the other end. That suited TCP at the time when it had one congestion response per RT, which standard TCP still does, but there are other forms of TCP around. So this is all about updating the feedback so we get all the feedback information, which is reflected in the title, which says the problem was congestion existence, not extent. And if you move to the next slide, the solution is congestion extent, not just existence, right? Accurate ECN is a change to the TCP wire protocol. The current proposal is it repeats a count of CE packets, or the data receiver repeats a count of the CE packets for that half connection in this counter called ACE that you see there in green
in the main TCP header, which is made up of 3 flags. It overloads the use of 3 flags that we use during the handshake, but it also adds an optional option which counts the CE bytes. And effectively what's happening here is there's counters for all the bytes of all the different code points on the receiver. There's counters for them on the sender. And the protocol is essentially sending the least significant bits of those counters across to synchronize the 2 counters with a round trip time and a bit of delay. Right. So sort of very simple conceptually. The reason for the duplication of the fields is that if the option is stripped, you've still got a sufficiently useful protocol in the main header with the ACE field, which already burns the headers to do the negotiation and the bits to do the negotiation. And the overriding requirement, if you like, of a number of use cases for this is to try to reduce queuing delay by having more information, more feedback information during a round trip time. And there's existent case of ones that give you 500 microsecond queuing delay over the public internet instead of the current state of the art, which is 5 to 15 milliseconds, something like that. Right. Next. So the changes in the last cycle, IETF cycle, I'm now going to go through, and the main one has been in response to a request from Michael Scharf to give justification for why we've designed the protocol like we have, why we've used the bits we have, and particularly why we've used the header bits. So there's 3 slides on this that reflect 3 new sections in a new appendix, Appendix B, put in the header there. And the first subsection talks about the justification for using them on the SYN. And the primary one is that this is how RFC 3168 ECN did its feedback using 2 of those bits, the ECE and the CWR. And the idea is to be able to fall back with, in other words, it's backwards compatible, so that a server uses the latest variant of feedback that it recognizes. So if the server doesn't understand ECN, it's an old server, it will see, it won't even look at those flags. Whatever they are, it will just be a no ECN server, and then the response it gives in the SYNAC will show the client that it doesn't understand them. If it's an 3168 ECN server, it will look at the last 2 bits, which do it, the ECN capability negotiation. It won't look at the 3rd one. We've tested, this is how they work. And so it will then respond as if it's an ECN server, and the client will fall back from accurate ECN to ECN. And if it's a full accurate ECN server, it will look at all 3 bits. And so you've got the backward compatibility in 3 bits. The need for the 3rd bit, or why we use a 3rd bit, other than this backward compatibility thing. Firstly, it was already allocated to the ECN nonce, which is now historic through a process we went through in here in this working group. And by combining that flag with the other flags, both in the handshake and during the counting phase, once the connection's established, you're actually getting 8 states. Whereas if you use that flag as a binary flag, you only get 2 states. So, it makes sense to not burn somewhere else and use that flag, because you're making efficient use of something that's already been used around ECN, and you're not burning far too much state in a very sparsely or a header with very little space. The original code point that the nonce used, we don't use in accurate ECN. There are, sorry, I got an email back from Anna, who did the measurement studies, who was looking at the data to tell me how many servers there were. But sorry, I haven't read it because I was dealing with another email. But it was something like 5 out of 26 million servers responded with that nonce flag. Well, either the server responded with it or something on the path changed it. And so it's sort of in the noise, but they do still exist, right? So we figure, I'm not sure waiting a bit longer will help if it is just random stuff, because you just get more random stuff, but
Gori first. It could also just be a broken implementation in a particular system that's got a particular front end, and you're never going to get rid of this. It's just going to exist as a small percentage.
So just to ram home the point I made earlier, if instead of using that third bit, we'd have done some other thing like use a TCP option to do this negotiation and reserve that third bit for some future protocol, as I said, it would only have been able to use that bit separately from the other 2 bits. So you wouldn't have got that benefit of the 8 extra states or the 8 states. And also would have had to put an option on a SYN. We've avoided that. Obviously, there's very little space for options on a SYN. And you've got the reliability problem of losing them sometimes because of middle boxes. And finally, would have had a protocol which had all this fallback in the old ECN in the header, and would have had an option and would have had to check for all the inconsistencies between things that might be changing one differently to the other. So we've had a more complicated negotiation. So overall, it was just much simpler, much more efficient to put use that third bit for the negotiation, given 3168 had already started using bits in the header. It's unorthodox to use bits in the header for this. TCP options would have been more orthodox, but it sort of makes sense. And I think this was why Michael was asking what was the rationale behind this. And I don't actually know. I don't know whether anyone does. I was involved in 3168 standardization, but I don't know the rationale for why things were done in the header rather than as options. Anyone know? Okay. Right.
I also don't know. Mia Kuleman, I also want to say that there was a proposal to use an option a long time ago, and I think the working group agreed to not go for that one.
Right.
So.
Yeah. Okay. I'll move on. So the second section of this appendix explains why we use these 3 bits in the SYNAC, these same 3 bits I was just talking about. And this has been since draft 04. We're now on 07. Well, actually 08 if you count my local copy. The idea here is that this table shows the SYN from A to B always set as 111. We're assuming the accurate ECN client starts that off, and then all the possible cases, all 8 cases of how those flags might be sent back. And we've ended up, since draft 04, using 4 of the states to reflect back what was in the IP header. I'll just finish explaining the table. The second block of states there are servers that do not support accurate ECN, this fallback mechanism I was talking about earlier. That's how the client recognizes those. And the last state is a broken state that we still found there's a reasonable number of these about, where the server reflects back whatever the client says in the reserved flags. And that's a broken implementation that's been around for some time, and there's less and less of them, but they're still there. Right? Okay. So going into a little more detail on why we've used all 4 of those states at the top there, because in earlier versions of accurate ECN, we didn't use those 2 shown in red to feedback ECT1 and ECT0. We only had a state to feedback whether there was not ECN, or whether there was another state to feedback whether there was congestion experienced on the SYN. And this was due to finding there was quite a bit of bleaching, which is why this slide has got white blobs all over it. Bleaching means wiping of the ECT code point in packets, usually going into the internet. And we believe this is a sign of bugged diffserv wiping, which is wiping the ECN field as well, because this stuff thinks it's all still part of the TOS byte, because people who write this code must be more than 50 years old, right? Right? And so, or they're reading books that are more than 50-year-old. So we've had to feed back the value of the ECN field in the IP header coming in. So the server feeds that back in the TCP header. And then similarly, number 2, the little sort of white number 2, we do the same thing on the ACK to feed back what came on the Synapse IP header in the TCP header going back, just to check both ways there's not this bleaching, right? Because if there is this bleaching, it's quite serious. You're sending ECN, you think the other end's negotiated with you at the TCP layer, and then you start using ECN, but it's getting bleached. And then the other end doesn't hear any congestion experienced that might have happened before it was bleached. For instance, in your a case would be a mobile broadband router in your home, then going over a mobile network that bleaches it, and you're getting congestion in your access link up to that. So we thought it's very important to make sure that both ends can detect this bleaching and then turn off ECN. Right? So that consumes the last 2 combinations of all possible 8 states in the SYNAC. And again, Michael was asking, do we have to do that? What's the reason for doing that? So we've written that in the appendix. I think Michael's, well, he certainly said he's happy with the appendix. I don't know whether he's happy with us doing it, but the other point about this is that state in column B marked nonce, and the other one marked broken. Although we've used up all 8 states, the nonce is potentially usable in the future if we want to have a variant of this protocol, and the broken state might eventually be usable as well. So we haven't really used up all 8. It's crappy middle boxes that have used up 2 of the 8. Crappy middle boxes or an old standard that never got used. An old experimental RFC. So they may become available later. Next slide, and that leads well into this slide, which is about what space there is for the future. And this was what Michael was particularly concerned about. If we're introducing a new protocol and then we find it's an experimental protocol, so if we find that it doesn't work or we need to change it slightly, how do we do a variant of it when we've run out of space for doing any statement that it's a variant, right? Any version negotiation. So we've written down what space you've got. You've got those 2 code points I just mentioned on the SYNAC, the one that was used by the nonce and the broken one. I think the nonce one would be usable pretty much now, given there's such a small amount of it about. The other one will take longer. Then there are 5 unused code points on the final ACK of the 3-way handshake. This part 2 of the previous one. That can't really be used. I'll finish the point. There are also 7 unused code points because there's the negotiation continues on the first data packet, or at least the checking continues. So there are 7 unused there. But by the time you're getting to the last ACK or the first data packet, you're not really negotiating anymore. You're just declaring. You haven't got any more cycles or phases of the handshake to agree both ends what you're doing. You're just saying what you are, so that you get limited ability to do version negotiation apart from those first 2 code points on the SYNAC. And particularly with TFO, if it's far too late to have done anything if you've already started sending data, or it becomes very complicated to unwind it all. right? But we've stated what the states are. They're in the RFC now, sorry, the draft now, and so in future, if someone wants to make a variant, it's clear what they can use. Then that first main bullet is about variants of accurate ECN. If in the other version of the parallel universes in the future, ECN, accurate ECN and everything doesn't come to anything, how can you reuse these bits? We've got 5 out of the 8 code points on the SIN are still unused. Could mean something else listed there. They would preclude any use of ECN at the same time. Certainly any fallback use. You might be able to sort that out with a TCP option or something. And all 8 of the code points in response to that are available. Actually, that sentence doesn't make sense. All 8 except 1. That means 7, doesn't it? Yeah, except 2. Yeah. So it's 6 of them. Right. Except the 000, which means I don't understand ECN at all, and reflection. Right. And then, of course, we've got 3 more TCP flags as well in the reserved area. Okay, so that's, I think, satisfied Michael and hopefully everyone else. I'll pause in case anyone wants to come up for a question.
Jana Iyengar. So, given that we have code in the internet that is 50 years old and still treats, ECN bits as part of the toss byte, what guarantee do we have that those 2 code points will come back to us?
But can you explain what you mean by come back to us?
What I'm asking is, I mean, I certainly don't know what the deployment for what deployment will look like in the future, but I'm not convinced that we're going to get the broken bits back. What you're suggesting is that we get these. Well,
I think the nonce ones are already in the noise. If you know, sure. Yeah. Right. So we got 1. Right.
So I think it'll be useful if we are specifying these 2 code points as potentially coming back, as what should happen to bring them back in the spec. That's what I'm asking for.
Well, you write an RFC.
Yes. I can speak to them. Okay.
Hi, Brian Trammell. Done some measurement on this. It's not like a really good longitudinal study, but we've done it at like several points in time. So along the time that we've seen ECN uptake going up and we've started seeing CE markings, the things that break ECN seem to be correlated with the things that break DSCP. So there's a lot of toss. No, he's talking about the IP bits. Which bits are you talking about? I thought you were talking about the bits in the IP header, not the bits in the TCP header.
Oh, I got confused by your question. Sorry. I was talking about the bits that
TCP header.
The TCP header bits.
The 2 code points. The first
2 code points that I was talking about on the SYNAC.
Yeah. The nonce and the broken one.
Just head down and power through. It's fine. Yeah.
It's fine.
So if you want to use those bits, you have to implement additional safety measures to make sure that you actually understand each other, right? But that's like a different protocol. I don't think we need to think about it right now.
Yuchun Chen here. I have recently explored a lot of comments about this proposal. So, but to me, is that I'm evaluating this proposal compare that with the DC-TCP ECN, which today it cannot work for a wide area because DC-TCP ECN requires you blindly trust the other end will do that. Because
You've generally got a slide on this next.
You haven't finished? Yeah. I'm sorry. Yeah. Go on.
Okay. Right. So this is a poor attempt to summarize all the discussion we've been having that Yuchun just mentioned. And I think the core of it is generic receive offload. And the problem that Yu Chung was about to describe, is that DCTCP has this step function in the network, and it generally gives you runs of CE for quite a long time, of congestion experience for quite a long time, and then runs of nothing for quite a long time. It sort of toggles on off. And so the way data center TCP does its feedback, it has a state machine on each end rather than counters that says, and every time there's a transition from a run of one type of, the marking on or the marking off, it changes the flag in the TCP header to the other and tells the other end. So you're trying to keep two state machines in sync by passing the transitions between them. And the IFC 7560, which was the requirements document for accurate ECN, had an appendix that showed that because this is all on, or a lot of this can be on pure ACKs, which you can never know whether they're lost. You're trying to keep two state machines in sync with an unreliable channel between them, that you never know whether the transitions have been missed, and so you can get the state machines out of sync because of a pure ACK loss. And they do eventually get back into sync, but you can misunderstand the amount of congestion in the meantime. So that was one of the motivations for designing accurate ECN. However, Yu Chung has been pointing out that with generic receive offload hardware, with these long runs of CE marking, with data center TCP, you don't get a state transition because there's a long run of it. And so the GRO hardware sees this long run, and it will allow it all to coalesce. And then at the end of the run, when CE stops, it will pass it up to the network, or once the cache is full, it will pass it up. Whereas with this counter, every packet, there's one more CE mark, so the counter changes. So it flushes the GRO cache every time, every packet, right? So Yu Chung wanted to use DCTCP feedback in the header flags, but otherwise use accurate ECN the same, use all the negotiation the same, or at least have the option of using DCTCP feedback. We've been discussing this off list, as we being Yu Chung and the authors and Neil. We haven't quite come to a conclusion yet. The arrows show where we've got to. We've got various suggestions to resolve the dilemma. One I sent this morning to that small group of people, and it needs quite a bit of thinking about, because I don't want to really think about it during the IETF, because it needs really working it all out, what its implications are. And otherwise, if we can't find a solution, it's because I really don't like the idea of having two versions of a protocol depending on what sort of pattern of packets you've got in the network. It just seems wrong, right? So we really do need to try and solve this problem with one protocol rather than two. But otherwise, we came up with, or Mia proposed, these three ways to accommodate the problem of GRO hardware. One would be two parallel drafts, which is the one that we all prefer out of the three, but none of them are ideal. It's the other two would be to have both mechanisms in the one draft, and because it's an experimental thing, we can try them both out using these initial counter values to find out which one you're using. And the other one would be to use the DCTCP mechanism within accurate ECN and get rid of the counters. But certainly we don't want to do that, because that was one of the main goals of the protocol, was to get away from that. So we are all committed to finding a resolution, but we're in progress. Yu Chung, did you want to add anything to that?
Thanks. That's a great summary. And I just want to add sort of my point of view is that it's always if I need to implement something or add more complexity to a stack, it's what's the benefit, and very practically. And I think accurate ECN would, despite the GRO issue, would handle under heavy ACK losses. It'd be far more accurate than DC-TCP. But the question I don't know is how critical is it to handle heavy ACK losses? And when I think of DC-TCP, it's like it's a congestion control feedback that at least Microsoft, Linux, and I believe FreeBSD all have. So it's a rather quick transition if we just need to use options or headers to negotiate that. And it does not have GRO issue, at least in the data center right now. So this is sort of, I'm committed to do more kind of data comparison work. If I can get an implementation of the ACE, or if I can come on my own, and let's look at some data, and so we can get a better sense of the trade-offs. Yeah.
And if I just, before Gori comes to the mic, if I can just explain that normally it'd be fine to just do this by experimentation and just bring out a new version otherwise, but because we're so limited on space and there's so limited ability to do versioning of the protocol, we're sort of having to do sort of either private network studies or desk studies or something to try and work out a solution based on what we think is going to be the problem, because we can't really do it on the internet.
That's right. That's why I because I'm burned badly because of the middle boxes issue on fast open deployment. Anything that has the least middle box concerns always looks very appealing, but I'm biased. Yeah, but I agree with you. We cannot test every single network and then, or make the protocol so complicated that it's just very hard to implement and deploy it. Yeah.
But you are not suggesting having two versions. One is one you prefer, the other one is both prefer.
So right now I have a slight preference of the two parallel draft, because that would just make each of the proposals simpler instead of trying to really glue the two together. But right now I really don't have very good data to make to justify my preference. It's just I'm always weighing towards simplicity and middle box friendly. I think some people here may not like me be, favoring middle box friendly. They will always say middle boxes are full and they should fix it. But the truth is they don't. So yeah.
Gori Fairhurst, I think I have to confess I'm now confused.
Okay.
And we spent a lot of time working on the accurate ECN proposal and understanding it, and we data center TCP in the meantime. I really feel very uncomfortable about the idea of having two different versions of this floating around that we're then trying to build new mechanisms on top of. So I don't know how we get out of this, but I'm interested in the discussion, and I think it would be good to make sure that everybody else who was interested previously understands that discussion as we go forward.
Just to maybe something is on the slide, but I didn't read it out, that the idea would be that Yu Cheng's version would have also have the accurate ECN option on the SYN, which would tell you that it was a different version than the other one.
Yeah. But
yeah,
I mean, we still have two different protocol machines going through the network, dealing with middle boxes in two different ways. One of which was trying to work in a controlled, constrained environment. One of which was targeting something slightly different. Both of which will operate really across the internet in reality when we get there.
Another point that Yu Cheng's point is that he wants his to also work on the wide area as well. It's not just for data centers.
But it doesn't matter whether he wants it, that will happen, I think.
Okay. Any further? Otherwise, Neil's coming up. We have one here.
Neil Cardwell, Google. I was wondering if if someone could comment on a possible approach of waiting until we have a specific congestion control proposal that needs this, that is far enough along that it has performance results demonstrating that this is definitely needed before we sort of try to finalize this proposal. I guess sort of going along with Yu Chung's comment, I have a similar concern about making sure that we, if we're going to undertake something with this level of complexity and possible middle box issues, that we are pretty sure that there's a congestion control that really needs it before we go too far down the road. And also, you know, if we deploy accurate ECN and then 3 years later in the development of L4S, we realize, oh, actually we needed something slightly different for L4S, that would be a shame too. So I'm wondering if maybe we should just have this proceed in parallel with L4S development, or if that's not a good solution.
So, I mean, obviously DC-TCP already needs it, but you're thinking something on the internet that needs it. Yeah. Is that okay?
Mia Kulevin. So for me, I think the best use case at the moment is actually ECN++. And deploying this together is an incentive to actually deploy accurate ECN. And I think it makes much more sense to try to get accurate ECN deployed now, because then you can actually eventually use your new congestion control on the internet. Because accurate ECN actually requires the other end to change, right? While your congestion control is usually just sender side. So you first need the feedback and then you can change your congestion control. So it's a deployment issue. And if we actually have a chance to get some deployment out there right now, that's better than nothing.
Okay, so we have chickens and eggs.
Yeah, going back to the deployment issue, I was also
Please say your name.
Going back to the deployment.
Your name.
Oh,
State your name.
Yes. So going back to the, I said my name is Manasi Deval. I work at Intel. Going back to the deployment issue, do you see accurate ECN being more robust than DC-TCP, or is there a comparison of robustness between the two?
You mean robust to middle boxes or loss or which?
Within a data center robustness.
Okay. If there's loss in the data center, then accurate ECN would be more robust.
Mm-hmm.
If there isn't, or well, actually, I wanted to add something to what Yu Chung said. That if you're getting some loss but not a lot, if say you get a long run of stretch act coming back saying the state machine hasn't changed, you don't actually know whether there was one in the middle of that stretch act that did change, because it may have got lost and then you wouldn't know about it. Do you see what I mean? It's not just whether there's loss, it's because you don't know about loss and you're using delayed acts and stretch acts, so you don't actually know. In other words, it's a non-deterministic protocol because you can't tell whether there was a message in the middle that changed things. So yeah, accurate ECN is more robust generally, but it has this GRO issue in a data center. Yeah.
Okay, and is GRO that interesting? Like, does it buy you any performance improvement that it must be solved?
Well, I can only go. I can believe what Yu Chung says, and I have no reason not to believe him, of course. But and maybe you want to say, yeah.
Yu Chung Chen. For fast networks, like we're talking about, say over 1 Gbps, GRO is definitely critical to have. For things like 10 megabits per second kind of links, probably not. But the trend is that the bandwidth is going up very, very quickly, right? And so I assume that GRO will become more and more important until there is a better solution that's being found. Like basically the offloading mechanism is becoming more and more critical, in my opinion.
And I would add that it is likely that if this protocol is deployed and it becomes used, that GRO hardware will be adapted to make it efficient. But it's just that, again, chicken and egg problem of what do you do in the meantime? Do you just have to throw more server resources at the thing because you can't use hardware optimization? You know, it's chicken and egg.
Okay. And the last question I had was about deployment, not just within the data center, but outside or across the entire network. Because in my understanding, all that traffic that you have on the wire would be tunneled. And therefore, you would need a middle box, not just to look at the outer header, but outer and inner header to be able to do accurate ECN. Is that something that's a concern for you?
Right, it is a concern, but it's not a concern for accurate ECN, which is an end-to-end protocol. That's a concern with the marking the outer tunnel, and there's a whole load of work in the TSV working group that I'm doing actually on there's been specifications for how ECN is dealt with by tunnel decapsulation since 2001, and they're generally deployed, but there's cases where they're not, and so yeah, that's a different question, but it's not an end-to-end question, because end-to-end you're out of the tunnels again. Yeah.
Thanks.
Yeah.
So one thing I just wanted to discuss a little more would be just sort of thinking out loud about this GRO issue. So the one possible strategy would be to say, if you want to use accurate ECN, you can use software GRO, which is definitely, it's something we use at Google, and I'm not sure, industry-wide how much people are relying on hardware for this versus software, but we could just say, if you want the latest and greatest stuff, then you need to use software GRO, which can presumably be, I'm imagining we could tweak it to be aware of the accurate ECN counting scheme and basically continue aggregation and just have a simple state machine to sort of make sure that it doesn't lose the information that's being fed back from the other side, but still continue to do aggregation, and then when it's got a full-sized aggregate, it can pass it up the stack with whatever accurate ECN bits attached to make sure that the full signal is passed on with aggregation. That would be one strategy.
And that would actually be very simple, because you'd just be having to run a counter in the software stack and pass up the result of that counter, including all the wraps. Yeah.
So going back to Neil, how easy is it to look at that and tell us what is feasible after thinking through, after being at the mic? Because that sounds a very interesting thing to look at and understand.
I'm definitely not the expert on the GRO code in the Linux stack. I think Eric Dumazet is, but I think it would be, the function that does the aggregation is fairly small and simple, and I think someone could do a quick experiment to see, what's the, how feasible would it be, how complicated and it would be to get it to be high performance, because it's definitely a very hot code path, and you'd have to look at the cache effects of that whatever extra state was carried along. But as Bob said, my intuition says you could probably do it pretty efficiently, because it's just sort of addition and some number of extra bytes for the state. Yeah.
Okay. Shall we move on to the last slide, which is next steps?
Okay.
So attempt to resolve the GRO issue. You can see that's work in progress. I think we're not at the stage yet where we have to choose between those three options. I think we're still working out whether GRO has a solution rather than having to do two protocols. I realized we hadn't acknowledged Yu Chung's contributions in the draft, which we will do. And I checked the recent contributions from Michael and Praveen. They're already acknowledged from previous contributions. So thanks very much. There's a next step, which actually I did this morning to address the outstanding issues from Michael, But then Michael's raised a further point, which I guess I need to bring up here, unless Michael's going to do it on. Is Michael on Jabber or whatever? Anyway, I'll channel for him. Michael is concerned that because this is a change to the wire protocol, the any passive monitoring going on of ECN, if it's not looking at the start of the flow, then we're changing the meaning of the bits in the flow, and that passive monitoring may be connected to systems that are doing, I don't know, load balancing, whatever, and our experiment may confuse those passive monitoring devices. Now, I responded on the list that I don't think we can say that's a problem for a protocol specification to say that you can't change the wire protocol ever, because there might be passive monitoring devices that don't work very well, that aren't looking at the start of the flow to see what this stuff means. And certainly talking to people who do passive monitoring, not particularly of ECN, they always look at the SIN anyway. You know, that's part of what you do to measure the round trip time and so on. So personally, I don't think it's a concern. I said that to Michael, he came back and said he still stands by what he says. And that's the state it's got to.
Hi, Brian Trammell. Do we have any evidence that anyone other than me has written software that does passive monitoring that needs? I mean, I've done it, but obviously, but and of course it does. It does the right thing and it's completely perfect. But
I'm not sure. Yeah. You know, Michael's point is they might be. You know.
Okay. Yeah. All right. Good. I mean, it would be. I would be happy. I would feel less lonely if I knew that other people were doing it. But yeah, it just seems like kind of a. I probably shouldn't come up here and call a bunch of my work.
It does seem unlikely, given there's not much. There's much CE marking going on. You know,
right. Okay.
So Brian, like your software isn't a problem because it's already broken, so it will not break anymore. No, because like if you count how often those bits appear, that's like useless information, and the information will change now, but it's still useless. So I think actually passive monitoring would be easier with accurate ECN, but like what I would put in the draft is a recommendation to, like, is it a recommendation? A warning to say that this is end-to-end. You should not do passive monitoring, right? That's what I would like to do.
And we have a section, I was thinking we should do that this morning. We have a section on recommendations for middle boxes and so on, and that would be where we'd put it. Yeah.
Jana Iyengar, I don't want to beat this down, but what recommendation are we giving about passive monitoring?
To be aware that the protocol might change, and to actually look at the SIN and see what's been negotiated before you measure the packets.
And therefore it might change, so they should basically keep up with the drafts.
Yeah.
No, I mean, I'm just saying.
The recommendation is
if we're going to write recommendations to middle boxes.
The recommendation is to read the draft if you're going to do passive monitoring, but you've got to read the draft to know that there's a recommendation in it to do.
So, I mean, there's very little that a passive monitoring device could do in this situation that would be a problem in a reaction to this signal, that would be a problem for end-to-end connectivity, where that middle box isn't already causing a problem for end-to-end connectivity.
I mean, I made
not a change in the failure, this set of failure states.
I made this point to Michael that if this thing is running some critical system,
it's already broken,
and it's not really checking the protocol, then it's already broken.
It's already broken in a way that you'd probably notice and have fixed it by now. So you don't really need the recommendation shouldn't be to read the draft, right? I mean, shouldn't say that in the IETF, but yeah, if you write it in the draft, it's hard for the recommendation in the draft to be to read the draft, because it's a little bit circular. You just crash the world. But I think that actually what should appear there is like, a paragraph or two showing thoughts on why, like exactly that reply. It's like why this is not a problem, right? Like that I think would be useful for the ISG to look at when this document makes up.
Actually, I didn't channel Michael correctly, because Michael's solution is that we shouldn't change the wire protocol. We should change accurate ECN so that it doesn't change the wire protocol.
I can't minute that.
Can you minute my silence at the moment? I'm trying. Okay. Yeah. Right. Yeah.
I didn't reply either. Yeah.
So, Gary Fairhurst, I'll try and do the minutes in a second. But this whole idea of monitoring in the network, you can look at this stuff in the network if you want to look to see if accurate ECN is being used, and that tells you it, and it tells you that there's feedback going on, etc. I'm not sure we should tell people not to do this. If you're deploying a network that relies on ECN, you should be able to at least track what's going on here. The issue I've seen appearing in some EU discussion with operators was, should people look at this signaling to actually gauge whether the network's broken? So there's a difference between counting ECN marks from accurate ECN and the whole thing about working whether the machinery works. And that, I think, is a more important recommendation. Please don't think an ECN mark with CE means your network's broken. It doesn't. That's the IP header bit. But if you look at the feedback, you also see it's on the other path, right? And that's the thing you shouldn't start assuming. So the feedback of this does not signal a problem.
One quick note in general. Michael just stated that he is not suggesting to change the wire protocol.
Not suggesting not to change it, or not suggesting.
Just one.
Okay, sorry, Michael. Yeah.
I just wanted to say, my name's Tim Shepard. I don't think we can, if it is the case that we can't change the semantics of the bits in protocol headers because passive.
Apparently, Michael says he didn't say that. So,
okay, but right, but I just we can't. If you're doing passive monitoring, you have to keep up with what people are doing and deal with it. You can't. I don't think we should change what we do to try to not. I don't think we should change what we're trying to do here or make any decisions because it might make it more difficult for systems that are doing passive monitoring to keep working. We should just move on. And the best thing we can do is just document what we're doing and be completely transparent about what the new thing is by having published internet drafts and RFCs, and that's it. So.
Mia Kulevin. So I think it actually would not even break passive monitoring, but I don't think that's worth explaining in the draft actually. But so if you do it correctly, not the way Brian implemented it, you would actually look at like when does the bit change, and then figure out that there must have been congestion. So if you actually implement that, then every time this bit changes, there's still this congestion. You get like more congestion feedback because it's accurate ECN gives you more congestion feedback. You still don't get the real accurate ECN counter, but it's a signal of congestion. So it would like if you do it, it would actually work. But
right, okay.
Jana Iyengar again. A small terminology nit. Passive monitoring has a lot of connotations which we might want to avoid. Not that it applies here, but maybe call it passive measurements. We've been talking about passive monitoring all this while, and we're talking about allowing it and encouraging it. So we should be careful to clarify exactly what we're talking about. It can be passive and pervasive.
Yeah. Okay, so I think we're working our way towards the last bullet on this slide. I'm not even going to ask about that because we've obviously got to resolve this GRO issue and things first. So I think we end there. I've just got a couple of things to add. One related to ECN++, which, apologies for letting it expire. We just ran out of time and we've got a meeting later in the week to edit it and get it sorted out. That's related to accurate ECN, so I thought I'd say it now, because we're recommending in the accurate ECN draft that it goes together with ECN++ in an implementation. And the other one is that I've got a presentation on the implications on rack on the on links and reordering in links in TSVWG. So there, it's a bit of a sort of heads up on that in TSVWG on Thursday.
Yeah.
Okay. Thank you.
Thanks so much.
Thank you. So here next.
Okay, so this is Yoshi. And today I would like to talk about my simple draft. The title is Disabling Pause when other protections are available. This is my individual draft. Okay. So let me start from the background of this idea. So as we already know, RFC 7323 requires putting timestamp in all segment. And then timestamp option consume 10 to 12 byte in option space. And then option space length is just limited to 40 byte. That means if timestamp option has been negotiated, timestamp option consume 25 to 30% of the entire option space. So it looks like it's kind of overhead to me. And then in the first place, why we need to put timestamp in all segment? And basically, timestamp has been used for two purposes, mainly. One is round-trip time measurement, but some research indicates that we don't have to measure round-trip time with every single segment. We just need several segments per round-trip time. It's good enough to get nice RTT measurement. However, in case of pause, in order to provide protections, we need to put timestamp in every single packet. So it's pause that requires put all segments with timestamp. So in other words, if we have protection other than pause, and then we don't need to put timestamp in all segments so that we can utilize option space for other purposes, saying it can increase TCP's extensibility, feasibility a lot more. That's the basic idea of this talk. Move to the next slide. Okay. So as I said, pause can provide some kind of protection. And then what can pause protect? So this try to illustrate how the pause protection works. Oh, I forgot to raise the point. And then let's say we have current endpoint here and here, and then establish TCP connection and exchange TCP packet. This brown rectangle indicate the segment connection to the current TCP connection. And in some case, some packet which belong to the current endpoint has been delayed significantly. And so since TCP secret number space is just 32 bit, if the delay is big, sometimes this, secret number is delayed more than 32 bits byte. And then when this packet goes to this current connection, it might be a little difficult to distinguish this packet and this packet. And then that's why we need a pause in this case. That's the prime case for pause. And then second case is previously this endpoint connected established to this point. And then, but this previous endpoint now disappeared. But still, the packet belong to this connection still exists for some reason. And then try to join the current, connections. In this case, if secret number somehow match to this connection, it's very difficult to distinguish this packet and this packet. And that's another case, pause need protection. And then third case is there is some malicious attacker somewhere and try to inject a packet and then try to do some, attack to this connection. So this is a third case, pause can provide protection if it's possible. That's the third case. Okay, move on to the next slide. Okay, so now let's take a look how pulse works. And basically, pulse use timestamp for protection. And what pulse does is compare the timestamp in the segment and then timestamp which received most recently. And then if timestamp in the segment is newer, then pulse think the segment is valid. And then the decision of which packet is newer or older is very simple. Let's say if we have two timestamp, T1 and T2, and then if T1 minus T2 is smaller than 2 to the power of 31, and then the timestamp T1 is a new one. Else, T1 think about its older. So it's a kind of binary decision. If T1 minus T2 is less than 2 to the power of 31, it's newer, but if else, it's older. And then this simple logic works for the first case, for all first case in the previous slide, for all duplicate segment in the connection. In this case, it works because timestamp value monotonically increase in a single connection. So this logic works properly in this case. And for the second case in the previous slide, for segments from previous connections, sometimes this logic works if the timestamp value monotonically increase across all TCP connections. However, in some implementation, timestamp value does not monotonically increase across all TCP connections. So in this case, this protection doesn't work. So in this case, for second case, pulse protection may work or may not work. And then third case, the segment from attackers. In this case, this protection won't work because, as I said, the pulse logic works just a binary decision, newer or older. So if the attacker uses random timestamp, then attacker's success rate will be 50%. So if attacker send multiple packets, probably one of the packets can cheat pulse protection. So in a sense, pulse cannot provide protection against attackers. So if we think this way, pulse can only be effective for the first case, and for second and third case, it's not very useful. So it might be better we have better protection, if possible. That's another motivation for this draft. Move on to the next slide. And then what kind of technology can be used as a replacement of pulse? And I think we have actually several technologies already. And so right now in TCP working group, TCP Inc. working group, we are discussing the technology that can encrypt the packet. And if we encrypt the packet, we can easily distinguish, packet belong to previous connection and the packet belong to the current connection because it's encrypted. So if we see all the connection from the old connection, packet cannot be encrypted, cannot be decrypted because it's encrypted with different key. So it's very easy to distinguish old packet and new packet. So it can provide stronger protection than pulse, much better protection. And then also in case of TCP, MPTCP maintains 64-bit sequence number space and in the session, and then it uses data sequence signal options as a replacement. So this indicates a sequence signals mapping, and then by checking, and then this information is sent to TCP option. So by checking this option, we can use this option as a replacement of the pulse, and then data sequence signaling check is much stricter than pulse because pulse is just binary check, newer or older. But in case of data signaling check, it requires exact match, so it's more robust and strict. That's why it can provide stronger protection than pulse. And then third option is TLS. This is application protocol, but it's encrypt the packet. And then we have seen lots of deployment in TLS these days. And if the packet is encrypted, just like TCP Inc., we can easily identify the packet belong to old connection and packet belong to current connection. So it can provide better protection than pause. So if these technologies are available, we can disable pause and switch over to the this technology for protection. That's the basic idea of this draft. Okay, move on to the next slide. And then also, this kind of new protection can have another possible benefit. So if you are running busy server, you might see lots of connection in time-waste state, and it looks like a kind of overhead, but this is necessary because time-waste state is required to avoid seeing segment from the previous connection with same endpoint. And then you have to wait 2 MSL time to be expired for this kind of connections. But this is not, great for the performance of the server. But let's say if we have new type of protection I have mentioned in the previous slide, and we might be able to recycle this connection in time-waste state. Because as I said, the purpose of time-wait is to distinguish packet from previous connection and the packet from current connection. If the packet is encrypted, for example, we can easily identify this is coming from old packet and this is coming from, belong to the current connection. It's very easy to identify. And then some people say, yeah, we have been used this kind of protection by using pause. But as far as I know, these days, this kind of protection is not used because we know there are several cases this, pause protection becomes unreliable. For example, if multiple client is behind the same NAT, it's used the same IP address, and then because of this, pause logic can be confused very easily, and then discard the packet unnecessarily, and that's cause the trouble. So because of that, some implementation like Linux disable this feature. So, but if we have new type of protection, even if the multiple clients are behind a single NAT, we don't have to worry about it. Packet is encrypted, so we can safely distinguish old packet and the new packet. So this could be another kind of benefit to use new protection. Okay, move on to the next slide. And so what will be needed? So since as I mentioned, the technology is already there. We have a draft and we have deployment of the technology. For example, MPTCP has been deployed. TLS is already deployed very well. And so what we will need is just to have some kind of signaling mechanism to enable this feature and then disable pause. That's what we need here. And then probably we need signaling mechanism because if we just disable pause without getting a permission from the other side, then packet might be discarded because RFC 7323 requires to discard segment without timestamp option. So if one side all of a sudden stop using pause and then stop putting a timestamp, and then packet might be discarded. But this is not what we want. So by using signaling mechanism, we have to make sure both sides agree to disable pause, and then after that, we can stop putting timestamp in a TCP segment. So that's why we need signaling mechanism. Okay, move on to the next slide. And so there are several ways to implement signaling mechanism. One way is define new TCP option and do negotiation during the something wrong. Okay, good. And so one option is define a new TCP option and use it the future negotiation during SYN exchange. And this is straightforward, but it requires another option space in SYN segment. And then the other way is extend timestamp option for future negotiations. And Richard previously, proposed this kind of idea. So maybe we can utilize his idea to some extent. That's another idea. And then third option is extend protection mechanisms. For example, in case of TCP, yeah, we might be use one bit of global sub option in ENO, and then in case of TCP Inc, we can use by using this one bit, we can negotiate if we want to disable powers or not. And in case of MP-TCP, we might be extend MP capable, or other way we can use MP experimental option in order for future negotiation. And that's the plan. And move on to the next slide. Okay, this is the last slide. Or you want to wait the last slide, or you want to speak?
Go.
Go. Okay, so this is the last slide on my talk. So as you know, this is very premature idea. But so at this moment, I would like to get the feedback on the 2 point. Does this look a promising idea to proceed, or do you see some serious problem or concern in this draft? And if this idea looks promising, what should be done to be adapted? That's the 2 point I would like to get feedback at this moment. Okay, that's the end of my talk. Please.
Okay. The previous slide seemed to assume that you've got to switch it off after you started, but in all the 3 cases you gave, MP-TCP, TCP Inc, and TLS, don't you know at the start that you're using them? So you don't have to start using pause and then stop, because you can just never use it. Yeah. Am I missing something, or?
You're also negotiating those.
Yeah.
So his
concern is if you aren't going to negotiate those, then you maybe want timestamps, right?
Exactly.
Right.
Yeah. But when would you turn them off during a connection?
When you realize these other ones are on, like you've got TCP going on, and you could say, oh, okay, then I can turn my timestamp off. I think that's what he's proposing.
Because you're negotiating it at the same time, and it might work or it might not. And,
yes.
Yeah, okay. Right. Okay. Okay. And if you don't mind, I've got another question, which is actually related to a case where you might have to turn it off later in the connection. Going right back, you said there's a 50% chance of an attacker beating this. So it strikes me that if you discover a case where you detect an attack with 50% chance, then you could turn it pause on to protect yourself in future.
But no, it's 50% chance the attack will succeed, right?
Yeah.
So before they find it, they might succeed.
Well, yeah. But then, yes, they may have. But can you succeed, or is it worth trying to protect yourself after the event? No. Okay. Right. Okay.
So, since he brought it up, I'll talk first of the your blind attacker protection. There's other protections as well. I mean, you have to guess the right sequence number, so it's not just the pause protection that's protecting you. I don't like this. I like timestamps, and I'll tell you why.
Okay.
Timestamps can be used for a couple other things. If you don't have any loss, you can actually use them as a unique identifier for extending the sequence number, if you will. If we made one minor change to timestamps, which you have a timestamp option change there, where you always, when you respond with a SAC, send the latest timestamp, then they would actually be an extension to the sequence space already, and you wouldn't have to worry about it. Okay, so I would rather see that happen than this. The other thing is, what I've been playing with our BBR implementation is I can look at the timestamp the other person is sending me through a series of acts, and if I can determine what timing value the person's or the peer is using, I can actually more accurately figure out what the bandwidth is the peer is receiving my data at. So the timestamp option is very handy to me, and I would not like to see it go away.
Okay. Let's say, Randall, let's say if you put the timestamp on the retransmit packet, and then you might distinguish retransmission packet. This is original packet, or this is coming from retransmission packet. So maybe that's what I'm thinking right now. Do you think it's possible?
Well, you need it on the data, and you need it on every packet, both ways, right? The data going out and the acts coming back.
But let's say if you have stored the all time transmission time in the local side, you don't need timestamp. You just
Yes, you do. Because
there may be a way.
If you've done a retransmission, if we had unique timestamps coming back on every act.
Yeah.
Okay. So if I send you an act, you send what was reflected back, I can then use the timestamp that I sent on that packet with the sequence number to determine which transmission it was.
Mm-hmm.
And it's a unique identifier.
Right. But it's not doesn't have to be timestamp. It's kind of some kind of unique idea.
You could use something besides a timestamp, but we have it there. It works. So why not use it?
Michael Tuxen from the floor.
Yep.
If I understand TCP timestamps correctly, so if you receive a packet from this old connection, then the TCP stack drops it. It detects it's from an old connection, and the ongoing connection is not disturbed. If you use TLS, you will end up in a decryption failure. And when the TLS gets a decryption failure, it terminates the TLS connection. So you don't get this protection. If I'm not wrong, anyone fluent in TLS? I think it's. I mean, if you decrypt, you get a. Yes.
Stuart Cheshire, I was thinking the exact same thing. To make this work, you would need some significant software changes that you give the segment to TLS. TLS gets a decryption failure, hands it back, says, don't acknowledge this, don't tear down the connection, wait and see if another one arrives. So it would be some fairly major surgery on boring SSLs to be able to reject segments without killing the connection.
I was just saying, you're basically correct, except I think you said it a little bit wrong. That you still get the protection of data getting injected into your connection. You wind up losing the TCP connection unless you are clever like Stuart, and I was having similar thoughts as well. So you're basically correct, but you still get the protection, you just don't get the robustness that you get. You get the protection from bad data, you lose your TCP connection. You're right.
Yu Chong Chen here is going to pretty much say the same thing, but and then to me it's like pause already works. It's not perfect, and now you say let's disable it and let the other layer do it, and or do some kind of cross-layer work, and that's needs a lot of work. And a further point is that even in your proposal of just no TCP timestamp on data, original data, it wouldn't work. Let's just use it. A simple case. So when you send this original data, I typically use the MSS without timestamp option, right? Let's say 1460. Now, okay, because of loss detection, you need to retransmit this one. You want to insert that 12 byte. That won't work because you exceed the MTU or the MSS. So you have to send the 1448 bytes in the first packet and the remaining on the next packet, or you require some kind of repacketization. And this is going to really hurt the TCP stack performance too. Yeah.
But sounds like an implementation problem to me.
We are IETF, right? Implementation problem is a problem.
Okay.
Yeah, I wanted to echo a few points and add a couple more. So I would, I'm a big fan of timestamps as well. I mean, I think Randall raised some of these points earlier that timestamps can be super useful when you have retransmissions, and they allow you to sort of quickly deduce that a retransmission was spurious. I take your point that there might be a clever way to not do the timestamps until you are doing a retransmission, but others have pointed out that could be problematic. Another thing that I haven't heard pointed out yet is that receivers actually make use of timestamps to do a receiver side RTT estimation in order to do receive buffer tuning, auto tuning. And there's not really another alternative that I'm aware of for receivers to get a good RTT estimate. And receive buffer auto tuning is, in my opinion, is a really important thing. So I think so I think, in my opinion, timestamps are really useful. Another another point would be that even though I do encourage folks to keep timestamps, I do see a potential value in either negotiating disabling pause or adding some bits that sort of allow each side to specify what they want the semantics of those timestamps to be. So, for example, I guess previously at IETF, we've discussed that our team is a big fan of being able to use microsecond granularity timestamps. And with those, really the biggest blocker is the fact that the other side might interpret those as millisecond granularity timestamps and apply pause semantics and then drop your microsecond tagged packets because they're wrapping too fast, essentially. So I do support a way to either disable pause or indicate that the timestamps may be advancing at microsecond rates and need to be the pause time scale needs to be adjusted accordingly.
So, in my understanding, you might okay with use new protection, but you don't want to disable timestamp option.
Yeah, exactly. I support either being able to negotiate pause off or negotiate some alternate semantics for the timestamps, but I do think timestamps are great. And I'm at least personally, I'm not worried about the loss in the option space because they do have such a nice semantics for detecting retransmissions, spurious retransmissions, and for doing receiver side RTT estimation.
Okay. Yes.
Hi, Brian Trammell. I'm just going to take the other side of that argument for a moment. I think timestamps are terrible. Not really, actually. I quite like them. They radiate an enormous amount of information about the internal operation of the transport, which in a lot of cases is good and in some cases is bad. And giving endpoints control over when they do that is a great idea. I'm a co-author on draft TCP timestamp negotiation. I'd be happy to basically dust that off and turn it into what we need for this. Because it was a little bit at the time, it was a little bit of a solution in search of a problem. And now it seems like it was a different problem, but it was not quite the right solution for the different problem. Because it was basically saying, okay, well, let's expose the timestamp generation rate so that we can do passive measurement of that without having to do, it basically reduced the amount of effort you had to do to essentially phase lock on the timestamp rate. Turns out when you phase lock on the timestamp rate, you get the drift of the clock on the machine, and making the drift go away so that you don't have linkability across multipath is really hard. So we know more about potential. So, in a lot of your cases, you don't care because you can already identify the machine by the IP address, but in some cases you might want to be able to turn that off. I think, that probably the right way to go about the TCP side of this is to look at TCPM timestamp negotiation, figure out if we want to tweak that approach or if we want to do something based on that approach, to sort of a generalized way to let the endpoint say yes or no in this case.
Okay. Thanks.
Thank you.
Thank you.
YouTube? Okay.
Hi, can you hear me?
Yes.
Okay, great. Hi, I'm Sohail from Google. Today, I'm going to present recent developments and extensions we have added to TCP Linux to make TCP faster and cheaper for applications. This is a joint work with Yu Chang, Neil, and many others at Google. I'm just presenting it as a cohesive story. Next slide, please. So when we want to deploy TCP on emerging platforms, 100 gig NICs, lots of CPU cores, the bottlenecks we see are usually inside application at the border of interaction with TCP. Namely, we need to optimize buffer allocation applications, but we can't really do that if we don't have proper signals from TCP. We need to save copies on send and receive. We need to get better notification of what is available in TCP. We need to somehow coordinate with TCP threads to basically try to preserve core affinity between user space and the kernel. And we need to lower per packet overheads on both receiver and the sender. So for example, the GRO mechanism that was discussed today a few times, we can't really get to 100 gig without having GRO or TSO either in software or in hardware. Next slide, please. Today, I'm going to present the zero copy mechanisms that are added to TCP in Linux, which we found very useful in increasing TCP's efficiency. Then I'll discuss a new feature called TCP in queue, which helps user space to optimize buffer allocation, and then I'll talk about user space threading and affinity and syscall overheads. With Meltdown and Spectre mitigations, syscalls are now way more expensive, so I will also discuss some mitigations for those. Next slide, please. So TCP's transmit zero copy was added by Willem in OpenStream Linux a few months back. It's a very simple mechanism. Everything works just like a normal Unix syscall. You do a send message for sending your data. The difference is kernel would keep references to your data blocks and send that data without actually copying that data block. And because of that, kernel would send user space notifications on when this block is not needed anymore by the kernel. Note that if it was just netperf or iperf, we could just allocate something and then unmap it and let the kernel deallocate the memory. But in real-world applications, these blocks are often shared with the application. For example, you can imagine a database with a memory cache, and these blocks are actual memory caches given to the kernel. So we need proper synchronization between TCP and the application. Next slide, please. The notification mechanism in Linux is very simplistic for any successful syscall, which basically means a positive number returned from the send message. We assign a sequential ID, and then when the blocks given to the kernel on that like on end syscall can be released, we just send a notification on the error queue. This is very specific to Linux, the notification mechanism, but we imagine it's easily extendable to other platforms. It's just a control channel. Error queues are basically for getting ICMP packets from the kernel, and then it gradually is extended for timestamps and all sorts of notification to user space. It's more of a control channel right now. We have a normal data channel for syscalls, and then error queue reacts for orchestration. Because there are so many caveats in the implementation, but user space should not touch the data payload while the reference is held in kernel. For example, you can imagine a NIC that doesn't actually have a checksum offload. If you modify that, if you modify the packets, it can cause data corruption. In the Linux implementation of zero copy, we have mitigations for this. For example, as soon as we see the packet is going through a device that doesn't have checksum offload, we immediately copy the payload and fake a zero copy notification. So user space see this as an actual zero copy, but we are actually doing copy inside the kernel. Next slide, please. Zero copy isn't really a magic. It says one copy adds extra notification to the app. So if you have just 1 byte to send, it's probably just cheaper to copy. And unless you have large chunks to send, it's not really worth it. But when you have like 500 kilobytes or 1 megabytes of data or 2 megabytes of data to send, using zero copy improves TCP performance by large margin. We see double-digit percentage of efficiency improvement. By that I mean how many CPUs we burn, how many CPU cycles we burn for sending the data. And we also save 20% of memory bandwidth, which can be a bottleneck on I got disconnected, I think, or can you hear me now?
Yes.
Okay, sorry. I don't know what happened. So on 100 gig, with 100 gig NIC memory bandwidth on the bus can actually be a huge bottleneck for TCP and the NIC. So by using zero copy, you can also save more than 20% of memory bandwidth. In our measurements, it's usually more than 30%, but we never saw less than 20% of improvements. Can you go to the next slide, please? This is a sender that uses zero copy. As you can see, you basically do a send message with message zero copy, and then you need to poll the error queue to read zero copy notifications, and then you can just free the blocks. I put it in the slides for reference if someone wanted to actually use this feature for the application. This code it's very simplified. It doesn't actually work for multi-threaded apps, and I will explain why in next slides. So there are some caveats on how to handle zero copy signals, but the idea is very simple. You just do a send message, you put your blocks with a sequential ID, and then you receive those IDs on error queue and release your blocks. Next slide, please. So one caveat of TCP zero copy is we cannot release a data reference in a packet if we receive the SAC for that block due to SAC reneging. So we need to make sure if the data is fully ACKed. And even if the data is fully ACKed, we can not release the packet because the problem is the packet, for example, I may have a spurious retransmission of a packet. The packet may sit on the device transmit queue for a long time while I receive the ACK of that packet. So a copy of that packet may sit somewhere on the end host. And for that reason, we basically need the signals are generated when we really don't need that packet, meaning that the data is fully ACKed and no copy of that packet is actually sitting on the end host anywhere. As a result of this, for zero copy, we may receive out of order notifications, which can complicate the release process in user space. But this is a decision that was made just to make sure the implementation in the kernel doesn't have too much overhead of handling, just coalescing these release signals. Next slide, please. So the next extension to TCP in Linux, we added this TCP in-queue. One of the problems we had on 100 gig NICs exchanging large amount of data was that the user space has to guess how many bytes are available in TCP receive queue. There is a syscall called FIO and read. You can call this to get the readable bytes on a socket. I think it is also available in BSD but the problem is right now after Spectre and Meltdown, these syscalls are very expensive, and when we do this, we can actually hurt a small data exchanges on TCP sockets. Also, we need to do that all per read, because while I'm reading from a TCP socket, there may be packets incoming onto that socket, and there may be more data available right after the read returns. So we added this to Linux. If you read some data, kernel will tell you how many more bytes there are to read. So, for example, you can call receive message on the FD. It will, with 1K, it would return how many bytes have been read, and then also tell you how many more bytes you can read. And using this data, we basically optimize the buffer allocation in user space. We allocate enough buffers and then because kernel guarantees that 65K is actually available to read, so we wouldn't over allocate. We allocate optimally and then read the data. We see 3% to 5% more efficient reads and writes for small and large RPCs with this mechanism. It also lowers the latency to a very good extent. Tail latency goes down because memory allocation can be a bottleneck when we have very fast NICs. Next slide, please. Another issue that we have is the emerging NICs are so fast and efficient that they're just packets being received on TCP streams. And if you wait over the event queue of a socket or a bunch of sockets, you're constantly receiving events from the kernel once every TSO chunk. And the number of wake-ups we have to do for a 100 gig NIC is actually very extensive. And each wake-up reads a few bytes, like 100 kilobytes, and then has to wait for another event to come up until we have a full frame to read. The problem with that model is that most applications cannot react until they read the whole frame. For example, an HTTP2 server cannot actually do anything until it has the whole frame ready so that it can process that frame. So what we did at Google is basically using receive low watts. So whenever we use a watermark to just basically silence the events until all the bytes we need for processing is available. This way we lower the wake-ups in user space for TCP. And while we don't receive those notifications, we can actually handle more useful notifications from other TCP sockets. And we can easily scale to thousands and millions of, hundreds of thousands and millions of connections just because we don't wake up spuriously. Next slide, please. This issue looks kind of clear and kind of obvious, but it's a very difficult problem to address. The problem is except when we have user space TCP, we have two sets of threads, one that actually does TCP processing and one that actually reads from the TCP socket. And if the data of a socket is processed on another core by TCP threads and then read on another core by a user space thread, we see more than 50% of throughput regression just because of invalidating cache and having to coordinate these CPUs. Linux uses very simple heuristics. For example, it used to set the CPU ID of a socket whenever you send or receive or poll a socket. That basically means I would expect the user space thread to read this FD on this core. So I would try to process a packet of this socket on that core. And the problem with that model was that, for example, if you have a Go application, there is only one poller. and all the FTs are pulled by one thread, and Linux would send all of the packets of TCP sockets to the same core, and then it would user space threads would read it from other CPUs. We removed this heuristic from poll and immediately saw more than 50% throughput improvement for those applications. But even with that, this expecting that user space would read from a specific core, no heuristic would actually work because a scheduler moves threads around. There is contention on these threads. Threads may get blocked on a CPU, get rescheduled. And we can't really pin all the threads for generic applications because there is a value to rescheduling threads by the scheduler. So instead of this, we actually changed our applications to orchestrate how they handle CPUs on cores to make sure TCP and user space threads try to process sockets on the same CPU. This is basically based on the heuristics we use for TCP in Linux, and then user space tries to follow the same heuristic, and they would basically converge to the same core. There's more than 10% gain as soon as we do this in efficiency and latency. But these mechanisms are not perfect because there are constraints that may move threads around. But this is a very difficult problem to fix unless we actually know what is happening inside TCP. So next slide. I think so. Based on this is just a summary. Based on the efforts that we had at Google to try to make sure TCP is as efficient as it gets on emerging platforms, we think optimizing TCP core like congestion control, making it resilient to reordering and loss is necessary. We can't really go to those emerging platforms without these developments, but it's not really sufficient to get ultimate performance for user space applications. The performance of TCP really depends on how TCP is used. For example, even how we poll the FDs, how the events are managed, how we allocate buffers. So we think there's value in looking on how we can provide more signals to the applications to make better decisions on how to use TCP. Some of the, for example, send zero copy, the reason that we copy is just the historical decision in POSIX. And we see large gains by revisiting those syscalls and adding extensions so that we can avoid copies, for example. This is implementation specific, but the heuristics that we use for Linux unsetting cores, for example, on poll, was based on a very specific application. And it really didn't look at a wide variety of applications that are actually using TCP. And that heuristic was actually hurting performance of user space just because we were not preserving core affinity. So we really need to make sure all these implementation heuristics are guided by how applications use TCPs at the moment. In this work, we use the old and new TCP metrics. For example, we have new transmit and receive timestamps in Linux that we use for trying to demystify latencies in different parts of TCP. Yuchang added a very nice chronos to TCP for Linux so that we can, for example, say, out of the 100 seconds this connection is open, how long we have been busy sending data, how long we have been receive window limited, and we use all of those in our research. Other tools such as netstat, SS, Linux perf, flame graphs, eBPF and ftraces are very handy in debugging these issues and making sense of the latency problems. This is the last slide. Thank you for your time, and if there's any questions.
Thank you. We have a short amount of time for questions.
Jana Iyengar, thank you for your presentation, Sohail. This is quite interesting. And thank you for discussing something that's different from just drafts and bits. So I want to ask, so you talked about various things, and on this slide I see the cooking large TSOs and so on. But to some degree, I think you're conflating workloads, and I would like to see if you can tease them apart a little bit.
Sure.
I specifically want to see if you can speak to which of these are critical for doing the web and video and internet-facing workloads versus data center type workloads. In particular, I am interested in understanding, and we've talked about this in the past, but I would like to see if anybody's tried to quantify the value or lack of value of TSO, for example, on internet or public-facing workloads. Specifically, because I know that Google uses FQ, and how much it actually plays into performance for delivering content. Can you speak to that?
Sure. Well, Yushang and Neil are, they have deeper knowledge of that part of the infrastructure. But for most of the things I talked about today are focused on 100 NIC fabrics and NICs on emerging platforms with like less than, in order of tens of microseconds of RTT. But except for zero copy, which actually can save single-digit CPU cycles when serving content to user space, especially content that has to be processed and it's not a static file. For TSO chunks, specifically for 100 gig NICs, we can't really saturate the NICs without a TSO, but that can cause congestions, as I think you have been referring to, for interfacing traffic or connections with lower bandwidth. So this is a double-edged sword, but for 100 gig NICs, having a full TSO sent out of the NIC without engaging software is a must. We can't really reach 100 gig without TSOs.
Understood. But just to perhaps rephrase my question, how much of this applies to internet-facing workloads?
Except for zero copy and polling. Polling and zero copy are important for just efficiency over many connections. So without the polling, for example, you can't reach more than 100 connections on a single poller. So you may have other better polling strategies, but without that RFS improvement, you can't really go beyond 100 connections. Zero copy is just, it's not a must, but it's just efficiency saving that would apply to internet-facing traffic.
Yeah, Neil Cardwell, Google. Yeah, just to add to what Sohail was saying and to address Jenna's questions. Yeah, I would agree with Sohail about most of these things being able to benefit internet-facing applications. And in particular, we definitely have experience with TCP zero copy helping internet-facing applications that send a lot of data, so video, for example. And then as far as TSO, yeah, so definitely TSO helps internet-facing stuff as well. Obviously, it's to a lesser extent, because for internet-facing workloads. Obviously, the bandwidths are not 100 gigabit. Obviously, they're closer to 10 megabits, 50 megabits, that kind of thing. But even at those lower bandwidths, there's a significant benefit from TSO. So, for example, the Linux TSO auto-sizing logic tries to create TSO jumbo packets or bursts, if you will, that are basically what it thinks are 1 milliseconds worth of data. So at 24 megabits, that's 2 packets. At 48 megabits, that's 4 packets. So between sort of at sort of 4K video rates, you can at least cut your number of trips up and down the stack in half by using TSO for internet-facing stuff. So we do definitely see value from TSO.
Thank you. Thank you for the presentation, Sahil. We go to the last presentation, Charles.
Okay, hello everyone. My name is Carlos Gomez. I'm one of the authors of the draft entitled TCP Usage Guidance in the Internet of Things. So basically, this will be a quick presentation, basically a heads up, as the chair said before, on the fact that the authors of this document think that it is getting ready to request a working group last call quite soon. So maybe some of you may remember that I presented the very first version of this document in TCPM back in IETF 96 in Berlin. And since then, after then, it was decided the home for the document would be the lightweight implementation guidance working group. So the document has been presented several times there, although Michael Scharf, who's co-chair here in TCPM and also co-author of this document, has been keeping the document, keeping TCPM in the loop through the mailing list. So our plan is to submit the next version, which will be 04, possibly a minor editorial update around September, October, and then request a presentation in Bangkok in both TCPM and also LWIC, and possibly around the time request a working group last call. So next, please. As a reminder, the goal of the draft is not to define a new TCP version, not to define new TCP mechanisms. The idea is to describe how TCP can be used, configured, or implemented in constrained node networks, which are quite typical in IoT scenarios, and present which are the related trade-offs. Next, please. So as a quick overview of the contents in this document, this is the table of contents. So after the introductory sections, we have section 3 that provides the main characteristics of constrained node networks that may be relevant for TCP, comprising node, network, and link properties, also usage scenarios and traffic patterns. Then section 4 provides TCP implementation and configuration in CNN's recommendations and content. So this is organized in 3 subsections. The first one relates with mechanisms or parameters that are related with path properties, such as MSS, ECN, and so on. Then the second subsection provides guidance for devices that are really constrained in terms of memory and can only afford very small window sizes, such as a single MSS window size. And the third subsection provides more general recommendations for devices that can afford larger window sizes but are still constrained. Then section 5 discusses how applications may use TCP connections and related aspects. Then we have security considerations, which are quite specific to this topic. And finally, we have an annex which intends to survey the characteristics of the main implementations of TCP for constrained devices. Next, please. So to illustrate this, we have a summary table from the annex, which intends to collect details on parameter settings and whether some mechanisms are supported or not, and also memory requirements in terms of code size for 8 different constrained, TCP implementations for constrained devices. So next, please. So again, the plan is to submit a 04 around September, October, then possibly request a working group last call by that time. And in preparation for that, it would be great if we could get your feedback, your comments on the document. So thank you very much in advance. I don't know if there may be questions or...
Any question? Nope. Okay, so then please provide feedback. Thank you, and see you at the next IETF. If anyone hasn't signed the blue sheets, please do so. And we are missing one, I guess.
Yeah.
What do you think about all the crazy optimization?
Yep.